In this second screencast on circles, we're going to look at tangents, normals, and so on for general circles. But we're going to begin with the circle centre, the origin, radius r. Now, last time we proved the following equation for the tangent to a circle at the point with parametric coordinates r cos theta, r sin theta, where theta was the angle that the point A made with the x-axis and r was the radius of the circle. So just by way of a brief recap, we noticed that the straight line O to A had a gradient which was tan theta, and so the gradient of the normal is minus 1 over that. If we then write down the equation of the straight line in terms of xy being a general point P on the tangent at the point A, then very simply y minus r sin theta is the y difference, will be the gradient of that straight line, which is minus cot theta times the x difference. If we rearrange and use the fact that r cos squared plus sine squared is 1, we get this standard equation for the tangent to this circle at the point A with those parametric coordinates. Now you can use that form to deduce the Cartesian equation of the tangent at that same point if you're given the Cartesian coordinates, in this case as x1, y1. In this case we can take exactly the same equation as before and notice that the point x1, y1, which is labelled as A, has x1 equal r cos theta and y1 equal r sin theta. So if we substitute into that parametric form for the tangent the fact that cos theta is x1 over r and y1 sin theta is y1 over r, we get this, and by multiplying through we get this as the Cartesian equation of the tangent to the circle x squared plus y squared is r squared, radius r, centre the origin at the point x1, y1. You can also generate this from the Cartesian form for the derivative dy by dx if you want. Now for a general circle we can use a very similar mechanism. So for example, if I take the circle in equation 1 here, which we've seen before, which we know has a centre minus f minus g, and it has a radius which is given by the square root of f squared plus f squared plus g squared minus c, by completing the square here, then we can determine the equation of the straight line, which is the tangent as shown to the point A with Cartesian coordinates x1, y1. And we can do that very easily because we can write down the equation of the straight line, which is this tangent, by saying that the y difference from P to A, which is y minus y1, it will be the gradient of that tangent times the x difference, which is x minus x1. Of course, the gradient of the tangent can be determined by the gradient of the normal. The gradient of the normal is this radius. And that's easy to work out. The gradient of the line CA is going to be the y difference, which is y1 minus g divided by x1 minus f. So this expression represents the gradient of the line CA. In other words, the gradient of the tangent at A is just minus 1 over this expression, and hence the y difference from P to A is the gradient of the tangent, which is this expression here times the x difference. If we rearrange 2, shown here in this form, we find that on the right hand side, if we put x1 squared plus y1 squared and 2fx1 and 2gy1 onto that side, we have an equation which is the equation of the tangent, but you notice x1 y1 lies on the circle. It's the tangent at that point that we're trying to determine. In other words, from the equation of the circle, x1 squared plus y1 squared plus 2fx1 plus 2gy1 will be minus c. So I can replace this right hand side by minus c, and hence on rearrangement we get this. So check the details from 3 to this boxed equation, but that's the equation of the straight line to that general circle, which is the tangent at the point x1, y1. Now, to determine the normal, either in parametric form or Cartesian form, for the circle that's centred on the origin, radius r, it's fairly straightforward, because we've already determined what the gradient of the normal is. We use the gradient of the normal, which would have been a radius, in order to determine the gradient of the tangent. So, very simply, for any point P on the normal, at the point A, which is perpendicular to the tangent, it will have to pass through the origin, and hence the y difference, say from O to P, divided by the x difference from O to P, which is y over x, will be the ratio of the y difference to the x difference for any 2 points. And if we take the origin as one and A as the other, then y over x is y1 over x1, or this. So that's the Cartesian equation, and we can substitute in that to get the parametric form, or the parametric form quite simply is shown in equation 1, because it literally says that from O to P, the y divided by the x difference is equal to the gradient of that normal, and the gradient of the normal, of course, is tan theta. For the Cartesian version, it's exactly the same as it was for the tangent, and in this case, for this general circle, we noticed that the gradient of the line from C to A will be the gradient of the tangent. That's that gradient, and hence for any point P on the normal, the gradient of the line from A to P, which is y minus y1 divided by x minus x1, will be just the gradient of the normal, which is this expression here. If you rearrange that, you get this, clearly a straight line. There's no more simplification really that can be done, and you certainly can't use, as we did for the equation for the tangent, the fact that x1 squared plus y1 squared plus 2fx1 plus 2gy1 plus c is 0, because that expression doesn't appear. Now, there's one very clever little idea that we'll use later on, and that's in order to determine the equation of the chord of contact, or polar line, which we'll define in the next screencast.